Hello, hello. This is 9.3, number 2, actually. I think it's actually number 2. I may have to be changing this at some point. But let's just go ahead. 9.3, I assume number 2. Now this has to do with specific heat. And here's the situation. Imagine you become reptilian. Now you have to be reptilian because we're mammals. We're going to regulate our body temperature. Our body temperature is not going to change whether it gets hot or cold. So for this exercise, we're going to have to say that we are reptilian and our body temperature is not changing. So your temperature has dropped to 15 degrees Celsius. And just like a reptile trying to find something to make you warm, you find a piece of steel, it's pretty warm, 80 degrees, and you get onto it. And the idea is the steel is going to warm you up. But as you are warmed by the steel is being cooled by your rather frigid body temperature. Now, the law of thermodynamics says that energy is not created or destroyed. So, it stands to reason that the initial energy is going to equal the final energy. And in this case, the initial energy of me plus the initial energy of the steel, Fe, is equal to the final energy of us together. We're going to have the same total energy. So, my initial energy would be my mass, 108.9, times the specific heat. Now, I don't know what the specific heat of a human being is, but we're mostly water, so we're just going to say it's the same as for water, 4,186. Our mass, our specific heat, times the final thing, my body temperature. Now, I'm assuming my body temperature is a cold day. I'm only 15 degrees. Now, add to that the mass of the steel. Now, the steel is pretty massive. It's 200 kilograms. That's the mass. Times the specific heat of steel is 445 times the temperature. It is 80 degrees, which is hot. Not so hot you're going to burn yourself, but pretty darn hot. Because after all, we don't want to burn ourselves. We just want to make ourselves warm. Now, I'm going to get hotter. It's going to get colder. I'm going to get hotter. It's going to get colder. And eventually, we're going to end up the same temperature. My mass is not going to change because I've warmed myself up. The specific heat of water is not going to change unless we boil it and make it steam. That's a whole other issue. And so the question is, what's my final temperature? By the way, that's also going to be the final temperature of the steel. The steel doesn't get lighter. It's not going to rust because of this. And that's the final temperature. Now, there is a shortcut. There is, I guess it's called the commutative property of math. I don't know. But don't quote me on that. Since we have the same common factor of the final temperature, I can take that out. And then we have 108.9 times 4186. That has been taken out. Plus 200 times 445. All right. Over here, same thing, same thing. So there's still. So let's keep going here. So multiply those all together, and I got. Okay. So this is the thermal energy of me is 6,837,831. Combine that with the thermal energy of the metal, 7,120,000. And that's going to equal temperature Celsius. These two, 100, my mass times the specific heat of the water is 455,855 plus the this is 89,000. If you're wondering about the two different kinds of brackets, I'm using two different kinds of brackets to reduce the confusion. These are a bracketed thing plus this bracketed thing inside these bigger brackets. That's why I said they don't actually have any meaning except for to say that this goes with this and not that, okay? That's all I'm doing there. Okay, going ahead here. Add these together. I get 13,975,831 joules. This is a lot of energy, but it's about as much joules as I use in a day. It's not a huge amount of energy. It's not an unthinkable amount of energy. And over here I get temperature Fahrenheit. Yeah, these together. So temperature, my final temperature, not my Fahrenheit temperature, final temperature. And 544,855. Now, to get temperature Fahrenheit by itself, we're going to divide by 544,855. 544,855. And I end up with a very reasonable temperature of 25. That's a 5. How do you like that? 0.6 is equal to my final temperature. Now, that was very complicated. It was a lot of numbers. I might have made a mistake, might I? So how would I reason whether or not this answer is correct? Well, things to think about. The temperature, if I'm the coldest thing here, and that's my temperature 15 degrees, if you put hot steel with me, we're not going to end up colder than what I started at. So it's got to be more than 15. On the other side, if you take this hot steel and you put a cold science teacher on it, it's not going to get warmer. So the temperature can't be over 80. So the temperature must be between 15 and 80. Does that qualify here? It seems to qualify. So does that prove it's the right answer? No. But usually when you make a mistake on something like this, you don't just get a wrong answer, you get a crazy wrong answer. And we did not get a crazy wrong answer. It is reasonable to believe that, in fact, our temperature is correct. Now, does this get me up to the normal operating body temperature of a science teacher? Not even halfway there. But if you're smaller, it might. Think about it. If you're smaller, the steel is going to be the same, the amount of energy is there is going to be the same. If you're smaller than me, then the chances are that you're going to get a bigger number than this because, you know, the smaller you are, the less energy it's going to take to heat you up. So smaller people, smaller students will probably have a larger number than me. Anyway, there we are. Have a nice day.